Okay, so we will be continuing our discussion of limits. And first we will look at limits involving trigonometric functions. And we have two fundamental limits that we're going to be concerned with here. And this is a limit involving cosine and a limit involving sine. And these come pretty quickly from the graphs of sine and cosine. So if we look at the graph of y equals cosine of theta, remember that cosine theta looks something like this. And this first result is just telling us that the limit as x goes to 0, or as theta goes to 0, of cosine of theta is equal to 1. And we can see here that as we approach theta equals 0 from the left to the right, the function of cosine theta is honing in on the value of 1. And then we have a very similar picture for sine of theta. But sine of theta looks like this, and we have a limit of 0 as theta approaches 0. So these are two trig limits that we will use extensively. And this is also kind of a classical result for trigonometric limits, and it's that the limit as theta goes to 0 of sine theta over theta is equal to 1. Intuitively, what this is telling us is that if we look at the graph of y equals sine theta, and we compare it to the graph of the line y equals theta, what's happening is you zoom in. So if you keep zooming in on the origin, the limit of sine of theta over theta as theta goes to 0 being 1 means that sine theta and theta are becoming more and more indistinguishable as you hone in on the origin. That's what it means for this limit of this ratio to be 1. So as you get closer and closer to the origin, it's harder and harder to tell the difference between this sine curve and the line, the 45-degree line, y equals theta. But this is a result that you can quote. This is a result that you want to remember, and so you can use this when you're solving different problems. For example, suppose we have this limit problem here, and this we will use that result, but we also will have to see here a technique. Anytime you see something like 1 plus cosine theta or 1 minus sine theta, these types of things, a good technique to try is to what we call conjugate. So we're going to multiply by 1 plus cosine theta over 1 plus cosine theta, and again, this is called the conjugate of 1 minus cosine theta. And that will help us, well, we'll see how that will help us. But this is a common trick to use. So with this, let's simplify. So the limit as theta goes to 0. And remember, when you're doing these questions, you always want to be writing carefully, precisely. You want to be writing your limit expression. So we have the limit as theta goes to 0. In the numerator, we have, when we FOIL this out, 1 times 1 is 1. But then notice the cross term will cancel. For the outer, we get 1 times cosine theta, so that's positive cosine theta. For the inner, we get negative cosine theta times 1. So those two cancel, and then we have minus cosine squared theta. And in the bottom, we still have theta squared times 1 plus cosine of theta. And this is handy. Recall, we have our formula of sine squared theta plus cosine squared theta equals 1, which means, so taking this identity, 1 minus cosine squared theta is sine squared theta. So that numerator will become sine squared theta. And again, in the denominator, we still have theta squared times 1 plus cosine theta. Now we will start to use our limit laws and recall our previous theorem. So remember, our previous theorem dealt with the limit as theta goes to 0 of sine theta over theta. And we can see that we have a sine squared theta here and a theta squared in the denominator, and we want to pair those up. So we want to try to use our limit laws now to simplify things. And we can break this up into the limit as theta goes to 0 of sine squared theta over theta squared times the limit as theta goes to 0 of 1 over 1 plus cosine of theta. And this works. Remember, we called this the product law because these two limits will show exist on their own. Then the limit of this product, sine squared theta over theta squared, times 1 over 1 plus cosine theta, is the product of the limits. Next, we can think of this as the expression sine theta over theta squared. And we can use our substitution law to bring the limit inside the square. So this will be the quantity limit as theta goes to 0 of sine theta over theta squared. And note, for this second limit here, well, we can use, first it would be our quotient law, then it would be our sum law. So this will be 1 over 1 plus the limit as theta goes to 0 of cosine of theta. We've just argued, well, we just stated that this whole limit here would have to be 1 over 1 plus 1, because as theta goes to 0, cosine theta goes to 1. We have our theorem that says this is also equal to 1. And so this entire expression becomes 1 times 1 over 2, or 1 over 2. Again, when you evaluated this limit here, you don't necessarily need to write this step. Often we call this directly evaluating. If you can plug theta in and you get something that gives you a limit, an existing limit, what you're really doing is using all the limit laws implicitly, but you don't necessarily have to write those types of steps. Another major topic in the study of limits is the squeeze theorem, also often called the sandwich theorem. And the idea here is, think of it as g of x being the function that you're given. If you have a smaller function and a bigger function, and it's the case that as x approaches a, the smaller function has a limit of L, and the bigger function also has a limit of L. For the limit as x goes to a of g of x, it is squeezed by the larger and smaller functions to having the same limit of L. This is most easily understood with a picture. So imagine, so here's A, and we'll have three functions, and say the blue function will be our top function. So that will be y equals h of x. And then we have to be a bit careful because we want to say here, the way this is drawn, the limit as x approaches a of h of x is equal to L. So now let's draw the lower function, which will be f of x. Now that's going to have this same limit of L. And then the orange function will be our g of x. But here's the catch. Based on this relationship here, the orange function, the g of x curve, has to always be between the purple curve and the blue curve for all x. Well, for all x in some open interval containing a. Let's just assume that this entire picture is contained inside that interval. So the point is, whatever this function does, it could get as crazy as you want, but it has to go through here. The fact that the top function and the bottom function have this limit of L as x approaches a, they squeeze the orange function, the g of x function, to having the same limit L. So this comes up a lot, in particular with sines and cosines. And so when we look at this, note that this function is undefined at 0. So the domain of this function doesn't include 0. And this sine of 1 over x will in fact get very, very jagged near 0. But the key thing to realize is no matter what the argument is, sine of anything is between -1 and 1. So we can start out like this, saying, all right, -1 is less than or equal to sine of 1 over x, less than or equal to 1. And let's see if we can come up with a string of inequalities that allows us to use the squeeze theorem. So note, x squared is greater than or equal to 0, which means we can multiply every term here by x squared and still maintain the inequality. So we get negative x squared less than or equal to x squared times sine of 1 over x less than or equal to x squared. And now we note that what we have here is the function that we're given. So let's now examine the limits of these. And we note the limit as x goes to 0, so we're looking at the same limiting behavior as we are for the given function, of minus x squared, and this is really the idea, this is going to be less than or equal to the limit as x goes to 0 of x squared times sine of 1 over x, which is less than or equal to the limit as x goes to 0 of x squared. And we know that each of these limits is 0. So what we can conclude here is that the limit that we're after, it's greater than or equal to 0, and it's less than or equal to 0. The only way that that can be satisfied is if it is in fact equal to 0. So this means the limit as x goes to 0 of x squared times sine of 1 over x is 0. using the squeeze theorem. A very standard squeeze theorem example, and again, anytime you see a limit where you have a sine or a cosine, it's usually worth considering using the squeeze theorem. Okay, the next topics, which we had talked about a bit already, is this idea of one-sided limit. And so we give two definitions here, which are very similar to the initial definition that we gave for a general limit. And so what we're saying here is, suppose f is defined on AC. So notice we're dealing with the limit as x approaches a, but we have this plus sign. What we're doing now is, if we're looking at a, we only care about what's going on the right-hand side of a. And so we're talking about the limit, the right-hand limit of f of x as x goes to a. And so this plus as a superscript is telling us exactly that. You just think about coming towards a from the right. And we say that that is equal to, that limit is equal to L if we can get as close to L as we please by choosing a point in this interval sufficiently close to A. So it's the same idea that we had for a general limit definition, except we're only looking to this right-hand side of A. Similarly, we also define the limit from the left. And so when we look at the limit from the left, we're looking at the interval from C to A, and it's just a mirror image of the picture above. So we care about approaching A from the left in this interval. And the limit definition is the same. If we look at an example, which we've already seen, remember we had seen that this was equal to 1 if x was positive and minus 1 if x is negative. People often will call this the sine function, not to be mistaken with sine, S-I-N-E. And remember the way we got this. Just take an example. If you plug in a positive x, say 2, you would get 2 over 2, which is 1. If you plug in a negative x, say minus 2, you would get minus 2 over 2, which is minus 1. And note, last time, actually, I think we wrote this in this way, but you actually have the same function. In either case, these two are the same. And when we look at the graph of this function, we noted, number one, recall that it's undefined at x equals 0, but it looks like this. And this is a case where we can look at right and left-hand limits. So if we look at the limit as x approaches 0 from the right of this function, when we restrict ourselves to this approach, we are honing in on the value of 1. In fact, we're equal to 1. So the limit from the right, note that we have this plus superscript for the 0. The limit coming from the right is equal to 1. You will also see some people use notation. People will often write the limit as x goes down to 0. Just in case you come across this. I probably will not use this in this course, but it is often used. Similarly, we can think about what happens as we go to x goes to 0 from the left. So we have the limit as x goes to 0, and remember, superscript is minus in this case. And we see, as we're honing in, as x is honing in on 0, the y value is honing in on negative 1. And again, in this case, is in fact equal to minus 1. So in this case, we have these different one-sided limits for this function as x approaches 0. And the natural thing to follow this up with is to say, well, these are different. If the limit as x approaches 0 of x over the absolute value of x, I shouldn't have written it this way. This was just the definition of the function. If we want the limit of this function overall, you would need to be honing in on the same value from the left and from the right. And given that these are not equal, this will mean that the limit as x goes to 0, the overall limit of x over absolute value of x, does not exist. And that's something that we're going to state now formally. So we have a theorem that says, suppose f is defined for x in an open interval containing a. The limit as x goes to a of f of x exists and is equal to L if and only if the one-sided limits both exist and are also equal to L. So this is just a generalization of what we were looking at before, but if you have a function, and maybe we'll draw it a little differently. Suppose it has a hole here, and the function value is down here at x equals a. Well, if you look, limit is L, this would be a case where the limit of f of x as x goes to a is in fact equal to L. And if you come in from the left, sorry, if you come in from the right, you see that the limit is L. If you come in from the left, the limit is also L. So the one-sided limits are both L, and that's going to be the same thing as the overall limit also being L. So the way that you typically use this is like we did in the previous example, where if you get different one-sided limits, you can conclude that the overall limit does not exist. So that's the most common application of this theorem. But it's a fairly intuitive idea. For the limit to exist, it has to be the same coming from each side. Thinking about one-sided limits, we also have to think about domains. So thinking of this function, root x, its domain is the non-negative real numbers. Working in the real number system, we can't take square roots of negative numbers. So in this case, we have the limit as x goes to 0 plus, so we're looking at the limit as x goes to 0 from the right, which is the correct limit to think of. Because the overall limit would not exist, so the overall limit, if we don't have that plus sign, it's not defined. Again, because we're not able to come from the left. It's outside the domain. We're just looking at the limit from the right. So we often have to pay attention to the function's domain when we think about these types of things, these types of limits as well, to be careful, to be mathematically precise. Another topic that we had mentioned, but we will now define formally, is this idea of a function having a vertical asymptote. So if a function is increasing without bound as x approaches a, we say it has a limit of infinity. Now this is a case of the limit not existing, but it's a special case where we can describe its behavior, this unbounded behavior. Similarly, if f of x decreases without bound as x approaches a, we say the limit as x goes to a of f of x is minus infinity. Again, these are both cases where the limit doesn't exist, but we're able to describe the behavior of the function, the limiting behavior of the function as x goes to a. A natural example here is 1 over x to the 4th. So let's draw the picture. And 1 over x to the 4th will look like this. And we know that this has this vertical asymptote of the positive y-axis. And this is a case where this limit doesn't exist, but we have this infinite limit. As x is approaching 0 from the right, the function is exploding without bound. As x is approaching 0 from the left, it's exploding without bound. And so we say this has this infinite limit. And by the way you can think of this intuitively, think of x being really tiny. If x is really tiny, x to the fourth is even tinier, substantially so. But that's a really tiny number in the denominator. So it's like having 1 over a trillion, which would be a trillion. So tiny numbers in the denominator make the whole expression large. This is one case. This would be this first case that we pictured here. If we had, say, minus 1 over x to the fourth, then we would have a limit of negative infinity. And again, this is a case where a limit doesn't exist, but we can still give it this name to describe its behavior. One last example, 1 over x minus 1. Let's draw this. And these functions, you can draw them fairly quickly when you think about this is just a translated version of 1 over x. So 1 over x has its problem when x is 0. This has its problem when x is 1. That's what results in a 0 in the denominator. So at the value of 1 is where we have our vertical asymptote, and it looks like y equals x. Just shift it over 1 unit. Now in this case, we want to think about one-sided limits, because as x approaches 1 from the right, the function is blowing up. So we would say the limit as x goes to 1 from the right of 1 over x minus 1 is infinite. So as x approaches 1 from the right, the function is exploding upwards. But then, if we look at the limit from the left, so the limit as x approaches 1 from the left of 1 over x minus 1, well, in this case, as we hone in on x equals 1 from the left, the function is exploding downward. And so we have a limit of minus infinity. And we can then say these two are not equal. So since they're not equal, so since these one-sided limits differ, the overall limit as x goes to 1 of 1 over x minus 1 does not exist. Because remember, for a limit to exist, you have to have the one-sided limits existing and both being the same. And in this case, they are different. But this is a different type of limiting behavior than on the previous example, because in this example, as x went to 0, we still had this non-existent limit, but it's blowing up to positive infinity. So we describe it in this way. In this case, we have this different scenario where the one-sided limits are not agreeing.